Morning everybody. Today we're going to start looking at nth roots of a complex number. So what I mean by that is if I had something like x cubed equals 8, then solving this equation tells me what the cubed root of 8 is. If I cube both sides, cube root both sides, I get x equals 2. So what we're going to be looking at today is, instead of using x's in this situation, we're going to be looking at some complex number z raised to some power equals something else. And by doing a method which is different to this, we essentially want to find out what z is. So we're not going to be able to just cube root things like we have been in the past to find, or fourth root or fifth root or whatever root it is. We've got to do something slightly more complicated to try and find out the values of z. But that's what we're trying to do today. We're trying to say, if I've got some complex number, what are the roots of that complex number? So let's start with some fairly simple. So first of all, I'd like you guys to have a think about what are the roots to the equation z squared equals 1. And hopefully you'll notice that I didn't probably need to use z. I could have used x there. So just quickly have a look at that one and come back to me, please. Okay, so there's obviously a few different ways you can do this. You could just square root both sides, which is probably the easiest one in this case, and you just get z equals plus or minus 1. The other way you could have done it is by doing z squared minus 1 equals 0. Factorise that because there's a difference of 2 squares. And from there you can see that z could be plus or minus 1. And this method is going to be more useful on the next 1 and 2, in the next couple of examples we're doing. Okay, before we move on to the next example, what I'd like you to do is try and draw fairly accurately the roots of this on an Argand diagram. So just quickly do that and then come back to me. Okay, so hopefully you've drawn those roots fairly accurately on an Argand diagram. You should have just got them obviously over here and here. Hopefully yours is a lot more accurate than mine. So next one I want you to try and do is z cubed equals 1. What are all the roots, real and complex, to that one? I suggest you start by taking 1 away first and then factorising some stuff out. Okay, so have a go at that one please, quickly guys, and then come back to me. So by taking the 1 across, you should get z cubed minus 1 equals 0. You know 1 is the solution to this, so z minus 1 is definitely one of the brackets, and the other bracket, if you sit down and work it out, was z squared plus z plus 1. That's all equal to 0. So one of the roots is z equals 1. Banging all this lot into the formula gets you z is equal to minus 1 plus or minus root 3 I all over 2. Okay, so again, not quite so easy this time. Can you try and represent those roots on an Argand diagram as accurately as possible, please? Thank you. Just pause the video, please. Okay, and the last one we're going to look at doing is just z to the 4 equals 1. I'm not going to do z to the 5, don't worry. And you can rewrite this obviously as z to the 4 minus 1 equals 0. That's the difference of 2 squares. Then you just got these two equations to solve. and essentially you either get z is plus or minus 1 or z equals plus or minus I. So if you draw that one on the Argand diagram as well, you get something that looks like this. And hopefully what you started to see is that you have all of these roots and they all have a distance of 1 from the origin. These have a distance of 1, these two had a distance of 1. For the other diagram you'd have had something like this. They've got a distance of 1 as well. So that's quite interesting in itself, the fact that they've all got distances of 1. That starts to make you think of circles because they've all got the same radius. The other interesting thing is the arguments that the roots make with the initial line. Can you just have a think about what the arguments are for each one of these? And I'm quite happy for you to guess what the argument would be for these ones. So obviously the argument for this one is 0 and then pi. The arguments for this one is 0. This one argument there is going to be 2 pi over 3. This argument here is minus 2 pi over 3 or 4 pi over 3. I'm just going to say 4 pi over 3 for now. For this one you've got pi over 2 and then pi and then 3 pi over 2. I've written them not negative for now, and the reason for it is because hopefully you can notice, well, the first one's a bit too obvious. It goes around pi and then pi more. This one is going around in 2 pi's over 3, back to 2 pi. This one's going around in half pi's, all the way back to the start. They all seem to be winding round. They've all got a modulus of 1. So if I said to you, for instance, can you draw on an Argand diagram the roots of z to the 8 equals 1, could you use this diagram here and possibly even a compass to draw me the roots to this equation on an Argand diagram? Have a quick go at that and then come back to this video, please. Okay, so hopefully what you got was this. Each one of these roots makes, well, this first one here has got an argument of pi over 4, and then they've got multiples of pi over 4 going round all the way back to the initial line again. They've all got a modulus of 1, so they all sit on this circle. And the really cool thing about these roots, if you hadn't thought about it already, is if you do a dot-to-dot thing, if you connect all the roots together, you get a nice geometric shape. You get a polygon, a regular one. And that's true for all of these equations. Anything which is z to the power of something equals 1, you get this really nice shape, and they all lie on the circle. You get polygons out of them, and what they're called is they're called the nth roots of unity. Unity because it's equal to 1. An important observation to make about these, in fact, just before we go on, nth root unity, generally we say that the first one is omega, so this root here would call omega, and then something which isn't too obvious just yet would then call this one omega squared, omega cubed, omega to the 4, etc. all the way around. We'll come back to why this is true in a sec. Omega to the 7, and then this is just back to the original, and just back to 1 again. So 1's always a root of these equations, and then we've got omegas and all the powers up to 1 less than what that power is there. If you look at these and think about them in terms of vectors, so if you think about this first vector here, which goes out here, oops, daisy, and then you think about this vector, and let's imagine I brought this vector over here. If I carried on doing this, this next vector takes me up there. If I carried on doing this for all of these, hopefully you'd see that you'd end up coming back round to where you started. So if I add all of these roots together, because they're vectors when I add them together, come back round to where I've started, that means that nothing's really happened. So 1 plus omega squared plus all the way up to, well, omega to the n minus 1 for, if that's n for instance, is always equal to 0. So for any equation, z to the n equals 1, if you add all the roots together, you just get 0. Okay, so what we're going to do now is just try and deal with a little bit about where these powers have come from, and then we're also going to look at how to solve equations where it's not equal to 1. Okay, so where on earth did that omega squared, omega cubed, omega to the 4 come from? Well, we know that omega is the first root here, and the full circle all the way around is 2 pi, and there's 8 roots altogether, so if I do 2 pi divided by 8, that will get me this first argument here. So I can write omega in modulus argument form. It's one lot of, and I haven't included the 1 because I don't really need to. So it's one lot of this bracket, this stuff here, and for the angle I've written 2 pi over n. So the argument is 2 pi over n. Okay, so what about the other roots? Well, omega squared is just a multiple of our original argument. This argument we said was 2 pi over n, 2 pi over 8 to be specific in this case. This one is just 2 lots of this. This one is just 3 lots of it. This one is 4 lots of it. It's multiples of that angle. And by de Moivre's theorem, we know, for instance, omega squared is cos of 2 times 2 pi over n plus I sine 2 lots of 2 pi over n. Or, for instance, if I want to look at a different one, omega 7, that's cos of 7 times 2 pi over n plus I sine 7 times 2 pi over n. So this side would describe accurately all of the omegas, all of the roots, because it's just multiples of the original one, 2 lots of it or 7 lots of it, however many times you want to go around. And using de Moivre's theorem, we can then translate this back to omega or omega squared or omega to the 7. Okay, so that's where those things come from. Okay, just for you, we do the next bit. Can you guys just do question 1 and 2? We've sort of done a bit of question 2 already. So exercise 10.2, can you just do question 1 and 2 before you come back to me? Yeah, just do those please and then come back to the video. Okay, so far this lesson has been just about the complex, the roots of 1. So for instance, we've been talking about z to the 8 equals 1. So that really is just the root of a real number, but the roots obviously can be real or they could be complex. 1 obviously is included within the complex numbers, but it is really just, well, we think of it as a real number, don't we? So let's live up to the title of the lesson a little bit and have a go at the nth roots of a truly complex number. So let's try one. So let's try find the roots of z to the 5 equals 1, let's say minus 1 plus I. Okay, so we can't just attack this the same way. We can't just say, oh, well, I know the roots are going to be of this form, and I can just write it out depending on what the value of n is, because this time I've got z to the 5 is not equal to 1. So what I need to do is use de Moivre's theorem again to get me going. So the first thing to do is write everything in modulus argument form. So the left-hand side of this equation in modulus argument form is r cos theta plus I sine theta all to the power of 5. And that's because I don't know what z is, so I have to write it as r and theta. The right-hand side of this one, I need to work out what the modulus in the argument is of this. So before we go any further, can you just work out what the modulus and argument of this is? So hopefully you can see straight away that the modulus is going to be root 2. And if you look at the argument, we're going around from here to there. Obviously we sit down and do this using trigonometry, because the opposite side's 1, the adjacent side's 1. Tan of theta equal to 1 is theta is 45 degrees, or pi over 4. So if that bit in there is pi over 4, then this bit here better be 3 pi over 4, and that's the argument we want. So we can write this as root 2 cos 3 pi over 4 plus I sine 3 pi over 4. Okay, so just to be sure what we've done so far, I've taken the left-hand side and written it in terms of r and theta, because I don't know what it's going to be, that's my unknown. And the right-hand side, I've just written in terms of its argument and modulus form. A better way to set this out, because I should have really thought about this before I started, would be write the question out, and then underneath that, say right-hand side modulus equals argument equals, do your working out for those two things, and then bring this line back in. So that's a real mess, that is. Okay, so we're into this situation. Now, this is difficult to deal with at the moment because the 5's on the outside, and what I really want to do is be able to compare the moduli and compare the arguments. So de Moivre's theorem to the rescue. This left-hand side, using de Moivre's theorem, is r to the 5 cos 5 theta plus I sine 5 theta. And that is still equal to root 2 cos 3 pi over 4 plus I sine 3 pi over 4. So now it's a case of saying to yourself, okay, let's match some things up. So r to the 5 is equal to 2 to the half, because the moduluses must be equal to each other. If I take the fifth root of both sides, that gives me 2 to the power of 1 over 10. Then I need to compare all of my arguments. So, I know that I want 5 theta to be equal to 3 pi over 4. However, if I solve this for theta, I'm going to get one argument only, and so I need to think a little bit more carefully about this. So the way to generate more solutions is by saying to yourself, okay, well, how often does 3 pi over 4 repeat itself? Well, if I went round the circle again, so in other words, if I added 2 pi to this, then I would get back to essentially where I started. Think about how these things work. If this was my first angle, if I go around 2 pi, I come back again. If I go around another multiple of 2 pi or another multiple of 2 pi, I always get back to the same place. So if I add 1 2 pi on, I'll definitely get back to where I started. Or I could add any multiple of it on. So I've got 2k pi in here. So k is going to be a natural number. I'm not sure why I put plus on there. Naturals are positive. So k is just going to be some positive number, positive integer. And so now to find theta, what I can do is I can divide through by 5. So I've got 3 pi over 20 plus 2k pi over 20. Okay, so how do I find my thetas now? Because I've got this k value in, so I've got 2 unknowns, I think, in this equation. However, k isn't unknown. I know that k was just saying, okay, if I go around once, if I go around twice, if I go around 3 times, if I go around 4 times, so I can just start going through those options. So for k equals 1, I've got theta is equal to 3 pi over 20. Well, so it's 3 pi plus, I should have started at 0, shouldn't I? Sorry. So plus 0 all over 20. So my first solution is going to be 3 pi over 20. My next one is going to be that k equals 1. So now I've got theta is equal to, let's just write this properly because that's bugging me. Of course, you can factorise it out if you want to. So now I've got 3 pi plus 2 pi over 20 by changing k to 1, which equals 5 pi over 20. So what I'd like you guys to do next, and that's what's bugging me, that shouldn't be a 20, should it? That should be a 5. And that's why I didn't write that together. Sorry, let's start that again. So for k equals 1, theta is going to be 3 pi over 20 plus 2 pi over 5. And hopefully that should be fairly easy to work out. That's 3 pi over 20 plus 8 pi over 20, which equals 11 pi over 20, which is much better. That's what I wanted. And then I can keep going. Can you guys keep going for k equals 2, k equals 3, etc.? And what I want you to think about is the fact that I said k could be any positive integer. When do you need to stop? So have a go at this, please, guys. Keep going. Remember that this is a equation which is to the power of 5. And polynomials have n roots for powers of n. So this should really only have 5 roots. So have a think about where you're going to stop. Try and work out the rest of the values of k, and then come back to the video, please. Okay, so hopefully, I can't remember if the k equals 2 or not before I paused it. So hopefully for k of 2, just assume you haven't got it, you've got 19 pi over 20, then you've got 27 pi over 20, then 35 pi over 20, and if you did k equals 5, you've got 43 pi over 20, which is the same as 3 pi over 20 plus 2 pi. And remember the first solution was 3 pi over 20. So these two are actually the same as each other. And that was k equals 0, 1, 2, 3, 4. So that's the 5th solution we get. So this one should go back to the start again because I shouldn't have any more than 5 solutions for an equation with a power 5 in it for polynomial power 5. One other thing to notice about this, when you've done these, and please always do them this way, but when you've done them, check that they actually are consistent amounts. Now, some people may have written their k to the fourth, sorry, k4 one as quarters instead. That's fine. However, you'll notice that it's 3 pi over 20. If I add 8 20ths on, I get to 11. If I add another 8 on, I get 19. If I add another 8 on, I get 27. There should be a consistent difference between them because of the way this is set up on the Argand diagram. Okay, so that should be enough for you guys to be getting on with. So what I'd like you guys to do is have a go at some more questions. So can you please go to exercise 10.2 again? And this time, can you do questions 3 and 4? I'm doing a Miss Hughes, I'm sorry. I think actually just go all the way up to 9. Right, I think 5, 7, 8, 9. If you want to have a go at question 6, but I'm not too bothered either way. Okay, sorry that was such a long lesson today. That's quite a complex, no pun intended, topic, and it needs probably a bit more explanation. Have a good day, hope that goes well, and email me if you have any problems.